So, welcome everyone. I hope you've had a pleasant evening so far. On this talk, I spent a lot of time looking into sort implementations, writing them myself, and a couple interesting things like I've learned along the way. And that's one of those topics. And that's the question of what kind of trade-off is there, or in this specific case, in this case study, when we look at sort implementations between safety and performance. And sorting, it's computer-based sorting. That's a famous problem, right? We've had computer-based sorting like for 70 years now. Like the initial computers they were written on, they were storing their bits in like circulating wires that were twisted and like twisted wire circling around. That's where quicksort was developed. So it's been a while. A lot of people have thought about it. A lot of papers have been written how to optimize it. So let's see. The languages we'll be looking at where we have some implementations are C, C++, and Rust. They all aspire to be low-level, or not necessarily low-level, but let's say systems programming languages that allow you to write low-level code if you desire to. A bit about myself. Klaus already said some stuff. Yeah, I write open source software in my free time. I'm a MUC++ organizer for many years now. I have commercial experience in building distributed systems, security critical software, and all this other stuff, right? But that's not so important now. I love reading from like fiction, books, scientific journals, everything. I enjoy board games and cooking, and I'm terrible at whistling. I just can't do it. So with that out of the way, let's look at the talk for tonight, what we want to talk about. At the beginning, I'll give you a motivating example that might explain why this might be relevant to you as well. Then we'll look at certain properties and how they are safety relevant and how, like, let's say, how they could occur in your code. Then we look at a bunch of implementations and how they are affected by these properties and how they handle them. Then we'll look at performance, we'll do some benchmarks and look at the results, and afterwards we'll try to draw some conclusions based on it. So let's come to this motivating example. At my previous employer, I was writing code for I was working on an internal compiler. I was taking a kind of intermediate representation, or like, let's say, a custom domain-specific language, and was turning it into language bindings. And as part of this code, I wrote this piece of code. I have a global constant. It's an unordered map. It maps strings to integers. I think you've written something like this in your code also. And I was developing it. It's a big feature. And then I open a pull request, and everything looks fine until the continuous integration tells me, yeah, it's all fine. Your local testing and tests look good, but the one pipeline we had built with many different pipelines, and one of them was address sanitizer, and one was memory sanitizer. Address sanitizer was like, yeah, it's fine. Memory sanitizer was like, yeah, this thing is being overwritten. This global value is being overwritten. So, okay, I start looking at the code. I go through the code, I look at it, and I'm like, that makes no sense. I'm not touching it. It's like, it's a constant. I never modify it. I look through all the associated code that deals with this variable. And nothing makes sense. Like, no one is overwriting this. So why is memory sanitizer complaining? Okay? I look at it with a very senior colleague of mine. We look at it together. We pour through the code. We can't find it. So, like, at this point, we're like, screw you, memory sanitizer. You're wrong. We're right. So we try to turn off memory sanitizer. We're like, don't consider this data structure. And memory sanitizer is like, no, still wrong. It's still complaining about the same thing. We're like, okay, screw you. We need to get things merged. We want to complete this feature. We don't have time for you. Let's turn off memory sanitizer for the entire module. Still, no luck. Okay? I don't know to this day if this is a bug in our way of turning it off or memory sanitizer was buggy. We don't know. But essentially, I looked at the code again and I discovered this. It had nothing to do with this data structure. Had nothing to do with this global variable. This thing is buggy, right? I'll show you the fixed version. That's the fixed version. And if I did this little fix, I took off this one character, and suddenly this global variable that is completely unrelated to this piece of code was no longer being overwritten. Okay, yeah, well, great. Why is that allowed to happen? The standard tells you it's undefined behavior. Why is that undefined behavior? So the thing that happens is the ordering of elements needs to be a strict weak ordering. It needs to form this kind of mathematical concept. And turns out, this is not that. That's not a total order. It's broken. It's not a guarantee you're supposed to give. And this was the fix. And the standard says, yeah, you're out of luck. We said you're not allowed to do that mistake, so clearly you won't make this mistake. The compiler is optimizing based on the assumption that you're not going to make that mistake, and you end up with weird errors somewhere else that cost you a week of time. Fine. Okay, so this is not just some theoretical thing. You run into that in a very quick, easy way to demonstrate. This is an entire proof of concept. All you need, that's the entire program. The flags to compile it at the top up there. You have a comparison function which follows some predefined set of orderings just to demonstrate what happens. This is what happens. Address sanitizer says heap buffer overflow, so you get out of bounds reads, out of bounds writes, endless loops. I've seen those too. So yeah, that's not fun, and it's quite an easy mistake to make. But okay, fine. I know you're going to tell me my code doesn't look like this. Okay, yeah. I don't write my code like this either. But how about this? Have you ever written this? That triggers undefined behavior. Okay, we can say maybe the type that's in the vector is some really weird type. Well, no, you didn't write that type, it's float. And if there is a none in the float, this total order is broken and all bets are off. You get undefined behavior. Maybe you get out of bounds, maybe you don't. You just get garbage ordering. Who knows? But this is not something that's entirely unfeasible to do. A lot of code looks like this, where you just sort vector floats. So I would say you might run into this. And in the experience other people have made, not only with floats, but with other factors where maybe you're comparing on two different keys based on a condition or other things. This is a common bug, and it's a dangerous bug because it runs into a really nasty kind of undefined behavior, out of bound reads and writes. So I would argue it's important. Because we're looking at different languages today, let's see what happens in Rust. If you just try to sort a vector of floats, well, the compiler tells you no, you can't, because the float doesn't implement this total ordering trait. But with enough, screw you, let me do it. You can get there also. You can just do this partial comparison, which can fail and give you back the answer, yeah, okay, those two are not comparable. If that's the case, just assume they're equal. That also breaks this total order guarantee. So it's not as easy to run into, I would say, in Rust, but it's definitely the same problem. It's user-defined code. You can't prove at compile time in Rust that something is a total order, and comparing things is safe to do in Rust, so somehow the implementation has to handle it, or it doesn't. Let's see. And this is a side note. If you need to sort something that contains floats, and you want to have a total order that actually makes some kind of sense, and you don't want to filter them out earlier, or you can't prove by construction that you don't have nones in your input, this is a branchless function for doing the comparison. It's quite effective, let's say maybe 10% perfect. When you have a good implementation, it's branchless, it's nice. Use it if you are in this situation. Don't just say, yeah, we parse user-defined files, there won't be a none in there. For example, Audition by Adobe, right? You put in a sound file that has nones in it, it crashes. So don't be Adobe. Let's look at another property. So here we've looked at ordering safety, and now we look at exception safety. That's something you've maybe heard about before. And the idea is, what happens if I throw an exception? Because exceptions in C++ are a common mechanism for error handling. The standard library uses it. It's also used for edge cases, maybe where you say, I do abnormal error handling a bit differently, but in this other occasion it happens. And let's say during the comparison, so we're sorting, not we, but the implementation is sorting our thing, and we throw an exception. This is valid C++ code, this compiles. What happens? In Rust, we have a similar concept. It's called panics. They also unwind the stack. It's not usually the way error handling is done, but for this talk, the important part is it's possible. What happens? And I hear you. No one writes code like this, right? I don't write code like this, but maybe you write code like this. Again, we're back to just you call sort, and v this time is a custom type. The elements inside the vector are the search query term thing. And they implement a comparison operator. This is where the user-defined logic comes into play. And we compare one tag to the other tag. Tags are variants, so we have either a string or an integer. That's fine. That's fine. But let's say 5 years later, someone else, the original person that wrote that code already left the company. Someone new is tasked with implementing this GPU-based index. They write it like this. The comparison function calls into a driver function. This driver function is a closed source binary blob. You just get to call a link into it. You get the headers. You have no idea if it throws exceptions. The documentation didn't say it throws exceptions, this function. Maybe it doesn't throw exceptions on your hardware, but maybe on some customer hardware, some weird old GPU doesn't implement that feature, bam, you get an exception. But you can't tell by just looking at this. And then you go back to this original code 5 years later, right? You're adding the GPU index to the variant. And suddenly this comparison down here, it may throw an exception now. So that's something where it's way less obvious that an exception will happen. And the question is, it might happen, so what will happen in practice? And in terms of exception safety, which kind of exception safety? So there are generally two kinds of exception safety. Basic exception safety, it promises you that when an exception happens, while it is unwinding the stack, you just don't get immediate undefined behavior just by the sheer act of it destroying values. Okay? And strong exception safety, it tells you, okay, we look at the operation as a transaction. Either you get to see the state before you try to do it or after, and if you get an exception in the middle, you go back to the state before. You can't have some intermediate state. And for a lot of situations, that's actually a really good guarantee to have, let's say. But I would argue for sorting, it's not really applicable. It's not really usable in a general purpose sense for like a standard library, and it might be too strong or not exactly what you want. For one, you'd have a performance overhead, right? You would have to copy the entire thing into a separate buffer and then roll that back after you've done the sorting, when the exception happens. You can do that, but you can't do it with move-only types. So suddenly, it wouldn't be a drop-in replacement for the standard library sort call. Another problem is this user-defined comparison function, it can do side effects, right? It might call a network function, and people actually do in sort calls, right? If you're the standard library, you can't get to choose how unreasonably you are used, right? People are going to use you, and you have to live with that. And you can't roll back a network call. So it's just not something that's compatible with the kind of thing we're looking for in a standard library sort implementation. The thing we're looking for, I've dubbed it intuitive exception safety. We'll look at it in a second. But let's first look at why basic exception safety might not be enough for you or might not be a good fit. In this example, we have a vector. We put in 2 unique pointers to nodes, and then we call sort. An exception happens. And afterwards, what you can actually observe in practice in quite a couple of the standard library implementations is that you will get values in a moved, some of the values, not all of them, some of the values in a moved from state. And a vector and a unique pointer in a moved from state, well, that's a null pointer, and suddenly you are dereferencing a null pointer. That's not great. So that's something that might happen with basic exception safety, right? As the catch completes, no undefined behavior, but some assumption you made because I put a pointer that's valid inside, when now it's gone, right? You didn't remove it, but the core code inside, the sort code removed it for you, moved it out into some temporary maybe, and then didn't move it back as the exception happened. Another thing that might happen, let's say you have integers and writing integers on top of each other, that's not undefined behavior, so that's fine. Something you might see in practice is you get duplicates. And at first glance, maybe that's not so bad, but maybe you have some follow-up logic. Maybe you have an arena allocator, something that has unique indices, tracks them, and then having duplicates might be a big problem for you, or might just break your logic or business logic. There's many ways in which this is not a, I would say, reasonable assumption that going into sort and getting out a different input than you were sorting, that's not what everyone assumes, let's say. So the intuitive exception safety we're talking about here is the sort operation is seen as a series of swaps. So you swap elements one at a time, logically, not practically. And when an exception happens, it interrupts the series of swaps. And then the element order is unspecified. You get some order, but you don't know what the order is. But you don't get some undefined behavior, or you don't get other elements. All the original elements are still present in the state they were, and they see all modifications, but more on that later. So let's come to this other property. mutation safety. This one's a bit more esoteric, so we'll go into it slowly. This compiles. You don't have to pass const references into the comparison function. You can just pass immutable references and modify the value. CVP reference tells you shouldn't. The standard, as far as I can tell, doesn't tell you anything about that. So is that right? Is that wrong? I would argue no one writes code like this, just exactly like this, where they just modify the value immediately. But the question is, what if it happens through some other more obscure way? Where, let's say, maybe you're implementing a JavaScript engine. Like there are JavaScript engines, actually all the popular JavaScript engines are written in C++, V8 from Chrome and SpiderMonkey from Mozilla. And you want to represent this root kind of object that's polymorphic and does some stuff. And what you're doing is called tiered compilation. So instead of immediately JIT compiling or some heavy compilation process, you interpret programs as they come in, because interpretation is usually fast to compile, slow to execute. And then as objects are used more and more, you go in and incrementally take pieces of your code and you JIT compile it, which is slow to do but fast to run. And this is what we have here. We have somehow want to store these in an aligned storage, so we can put them in the same memory location. And we'll have this object handle class, which is a view into this data. It's not a owning view. It's just an owning thing. It's just a view that gets to be easily passed around, copied. And what you have is a pointer towards one of these objects, and it can be either a interpreter object or can be a JIT object. And what we also do is pointer tagging. We take the most significant bit, we write a 1 into it if it's a JIT object, and if there's a 0, as usual, then it's the interpreter object. So that's a kind of technique. It will not work on every machine out there. It's just assume it's Linux 64 bits and it works. What happens is nothing bad happens here, I would say. Maybe, maybe not. But let's see what this eval function is doing. That's a bit more complicated. I'll go through it. So we have this function, which is, we have the construction, we have this JIT opt object function, which either gives us this JIT object pointer or a null pointer based on whether or not it is that object in the state. It's a bit like a variant, but we are storing the tag in the pointer. It's an optimization technique that some people do. And this is the evaluation function, which turns the value, the object, into some concrete value it has at the current time, which might then be used at some later point. And here what we're doing is we are calling this JIT opt object function, and it gives us back a pointer, either a null pointer if it's not that object, or if it was tagged to be a JIT object, then we get back a pointer that's cast into this thing. We call evaluate on that eval, and we're done. Otherwise, if it's not that JIT object, then we interpret this pointer as a pointer to an interpreter object, call eval on it. And what now comes the interesting part. We have a internal counter that keeps counting up on each usage. And if the usage reaches some threshold, we say, okay, that object's hot. We will promote it by compiling it with the JIT. What we do is we construct a new JIT object. We destroy the old value, we placement new the JIT object into the same place the pointer was in, and we tag the pointer, the internal, this underscore object thing, we tag it to remember that we are now a JIT object. One last slide, I promise. It's a lot of code, I know. And this is the outer context. This is how all these things get created. First, we have some kind of maximum amount of objects that we can allocate. We reserve that, and then later on when we create new objects, we create these object handles by pointing into that allocated memory. We never reallocate. And this is essentially a arena allocation. We have two vectors that lay, and we have the fast storage where we store all the objects, and we have the handles that are cheap to copy, cheap to move around. Okay. Let's come to the sort-related thing. We have this sort function. It's const. It sorts the handles, not objects themselves, it sorts the handles. And what it does, it calls evaluate on each, it calls eval on the objects themselves. So this is the eval function we looked at earlier, this one. And if the implementation of sort is not mutation safe, well, then we get undefined behavior. But where and why? Is anyone here willing to guess? I can show you the slides again. This is probably the most interesting slide here.
Because the equal might not be, or the less operator might return a different value if you hit the object in the meantime. You cannot guarantee any more order.
So you say you might get a different order because it's a different value. I mean, we don't have the code for like how the JIT object is created and whatnot. So let's assume it has the same semantics. So like it's compiled as a JIT object, but the value semantics it has for the comparison stay the same. So that's not actually what I'm looking for here. Anyone else willing to guess?
At some point you're going to compile the object, make the JIT object, then another value will be called later.
Yeah.
Some of that path. According to your usage count will go up.
Yeah.
Then you swap the object and then you go to the other path.
Yeah.
And then, yeah.
But like, why does that blow up? Okay, let's look at it. So let's imagine we are inside the sort implementation. And usually a lot of standard library code, what it does, it is specialized on the properties of the type. So for example, if a type is trivially copyable or has no except move, these kind of things, the implementation changes. You have different code paths that get executed. And here, the T, as our object that we're sorting, is this object handle, and it's essentially just an integer. If you look at it in the definition, it's just this mutable uint pointer type object. That's literally an integer. And what happens is maybe during partitioning, we make a stack local copy because that's more performant. We don't want to re-reference the thing in the on the heap because then we go into aliasing and we need special optimizations. So what we can help the compiler to prove that those don't alias by copying it onto the stack. And then during the partitioning, let's say we scan through it and we partition, we call the evaluation function all the time. And we'd call it with the stack value, with the stack copy of the thing. And the stack copy is the thing that will see the mutation to this pointer tagging. So this pivot that we have here, it gets tagged and then discarded. And then later on, when we call, well, maybe we have partitioned the thing once, and then we need to do more work. And then in the vector, the value that remains is untagged. But underlying it, we have changed out the interpreter object to a JIT object. And now we're calling the eval function of an interpreter object on the state of a JIT object. And what this means is type confusion. It's called type confusion undefined behavior. And it's not specifically this bug, but type confusion in general is a very dangerous kind of undefined behavior because it leads to 100% reliable exploits. And the V8 engine in Chrome has run into like some of the highest scoring CVE bugs they had was because of type confusion. Because type confusion means usually the user controls the layout, not the layout, but like the content of the thing that's being interpreted in some kind of other way. And maybe it's just some harmless integer that the user controls. But if it's executed as, like, if it's interpreted as something completely else and used in logic, maybe that integer that was maybe just, let's say, a JavaScript integer now turns into a function pointer. And so they can control things. And these are very dangerous kinds of undefined behavior. And as we see, the chain of reasoning needed to realize why that's a problem is not trivial. So I'd say mutation safety is something that might affect you, and it's not always totally easy to see why it would happen. So it's not as simple as, okay, if something happens, I change the value. There's many more links and chains in between that might not be as obvious. And if you see this eval function, it is const. And this sort function, it's also const. Why it's possible to mutate them is because of this mutable keyword, which allows us to mutate through a shared reference. Just as a little side note in Rust, it's also possible to mutate value through a const or like shared reference, how they're called. But you need a special type. You don't use the word mutable. You use types like cell or mutex to do the same. But essentially, that's the same code in Rust. So implementations written in Rust need to care about the same kind of issues that C++ implementations need to care or can care about. Let's put it like this. So a little recap on all these properties we looked at. With ordering safety, I would say this is the one you run into the easiest, and that's the one you see the most often violated. And the question is, what happens if the order is not total? Exception safety asks the question, what happens if you unwind the stack during sorting? And mutation safety asks, what if the element is mutated while it is being sorted? So I looked at a couple implementations, in this case only unstable sorts, and we have a couple. We have C-based ones, a couple C++-based ones, a couple Rust-based ones, crumb sort by Igor van der Hoeven. This has an interesting issue with the API we'll talk about in a second. Also, it's written in C, so it doesn't have any mutable or stack unwinding by default, but you can compile it as C++ code, so those issues then become relevant. We have the lib standard C++ standard sort implementation, the lib C++ one, the Microsoft one, PDQ sort by Orson Peters. It's quite interesting here because I think 3 or 4 of the other implementations on this slide are derived from this one. It's quite impactful in that way. IPS4 is focused on multi-threaded performance and multi-threaded sorting, but it has a version by the authors that is single-threaded only, so it's interesting in that way. Block quicksort is interesting because it popularized branchless partitioning, which was then picked up by PDQ sort. Crumb sorters is a port of the crumb sort code to Rust, quite verbatim. There's also some interesting caveats we'll talk about. We have the standard library implementation in Rust, which is a port of PDQ sort actually, or derived design. We have DM sort and IPN sort, which are also derived or sometimes novel implementations. Yeah, so let's look at the properties. I measured all these different properties. And the first property I looked for was functional, because I don't care about an implementation which doesn't work, right? The fastest and easiest way to sort is to not do it. Then it wouldn't be functional, so I don't care about that. So I want it to be functional. It has to actually produce correct results, otherwise I don't care. The next column is about it being generic or not. And the C-based implementation, it has an issue. It has the issue, it's written in C and the interface is C, so C doesn't really have something like template instantiations and things which allow the user-defined code for the comparison function to get inlined. So user-defined functions are passed in as function pointers. And unless you're doing some really fancy optimizations, these will not be inlined. And the fact is, that's quite slow. So what did the author do? They have 2 different versions of crumb sort. One is they have one that takes in a function pointer like qsort. It's quite slow. And the other one is you define a macro before you include the file, and that macro is your comparison function. And then it gets instantiated via macros, essentially. But that means you only get one comparison function per compilation module. That's not really generic. Also, you need to modify the source code to get things that are larger than int, or like 64 bits usually. That's also not so great. The IPS4 and block quicksort are not really generic because they don't support move-only types. And crumb sort RS, the Rust port of crumb sort, it doesn't support types that are not trivially constructible, copyable, and destructible. It does this limitation on purpose, so it can do things where it just treats everything like integers. It's just copying values around and doing things like this way. This allows it to do a lot of porting of the logic of crumb sort to Rust without going into the unsafe territory of writing it in unsafe code. But the effect is actually interesting that it doesn't have these ordering safety or exception safety properties. The effect will not be instantaneous undefined behavior, but you will get duplicate elements, for example, which can have later on trickle-down effects. And it can't be mutated. The type system doesn't allow it, so it doesn't score in that area. The other Rust implementations are interesting, actually. They're all written using, in parts, unsafe Rust. So they use a subset of the language which allows you to interact with pointers and things that are unsafe. So you need to prove yourself in your head or in text that the thing you're doing is safe. The compiler just says, you told me to not check, you do it. It allows more flexibility. We also see another effect is that pretty much all implementations in C++ don't provide ordering safety, nor exception safety, but they provide mutation safety with the exception of IPS4, which interestingly does not provide mutation safety as the only C++-based implementation, at least the first kind of mutation safety. The second kind of mutation safety, we see a 1 and 2 here. The second kind, it asks the question, what happens if you mutated the value and then you throw an exception, do you actually get to see the modification you were doing? And the interesting part is here, we have a Rust-based implementation, the MSort, which proves that you can have exception safety and mutation safety in isolation, but doesn't mean you will get them in combination. Just by having them in isolation doesn't give you the guarantee in combination. That's an interesting find, I think. So you need to actually care about in your head, you need to think about unwinding paths. When each time the comparison function is called, the stack might unwind. Do you have made any temporary copies? You will need to write them back. That's essentially what this boils down to. And crumb sort written in C, we can't really fault it. It doesn't have mutable, it doesn't have exceptions. But you might run into these problems if you compile it as C++ code. This is why we look at it in this way. And otherwise, we see that pretty much only Rust-based implementation managed to give you all safety properties. None of the C++-based do, and that's not because they can't, they just don't. It's possible to have all these properties in C++ as well. And interesting also a little bit in there is that in last year, there was a security thing around glibc, that's the GNU, or like for most Linux systems, the C standard library, and qsort is implemented in there, and they wanted to be ordering safe, but they weren't because they wrote their code in a buggy fashion, and they fixed that bug. So like they thought they had ordering safety, but they didn't have it in certain situations, and they considered that a security critical bug, and the C people fixed that. So it's not just Rust people that care, C also cares. Even though it cost them 1 or 2%, I think, in performance, they were like, no, we want to have that, and they changed it. So let's look at I was talking about performance already a bit. Let's talk at more details, more benchmarks. This is the system I ran this on. I did these benchmarks a year ago when I initially wrote about this topic. We'll do some later we'll do some more benchmarks on a newer set of software. I always picked Clang or GCC depending on which one gave the better performance results for the C++ and C-based implementations. So it's a best case scenario. It's a moderately modern AMD CPU. So let's look at how we measured things. One very important thing for sort implementations is that they are adaptive. So if you have a kind of pattern in the thing you're sorting, they can exploit that. So for example, if it's entirely sorted already, you can scan through it once, and then your ON, you scanned it once and you're done. You're like, oh yeah, it's sorted. I don't need to do anything more. And that's faster than actually sorting it, obviously. And it happens a lot in real code, like calling sort on things that are already sorted. If you instrument real-world code, that happens a lot. Descending is just the same, but reversed. Random, that's cryptographic level randomness. It's just really unpredictable. It's the worst case for the branch predictor. Random D20, that's a low cardinality distribution. You have 21 distinct values and uniformly distributed from 0 to 20. Random P5 is a bit of an extreme case where you have 95% of 0, all the same value, and 5% mixed in non-uniformly that are random values. Random S95 simulates a different scenario where you have, let's say you have a vector and you sort it, okay? And then you add some elements at the back, because vectors usually you add elements at the back, not in the middle. And then you call sort again. And maybe you didn't replace all the values, but you maybe just you added 5%. And so it's nearly sorted, but there's a small part that's not sorted. And that's an interesting pattern. Some implementations exploit that, some don't. And the last one is a SIP distribution. These are commonly known as 80-20 distributions, where, let's say, 20% of the values make up for 80% of the frequency. And these are actually more what you'll see when you talk about my data is random. This is what you'll see in the real world. It's not cryptographic, purely unpredictable randomness. You actually get something that's more like a Zipfian distribution. And the 1 means it's a characterizing exponent of 1. All right. I'll drink a bit of water. I'll let you look at this, but it's small. Don't worry. I'll talk about the bigger picture here. You don't need to look at all the numbers. Yeah. On the x-axis, we have time in microseconds to sort 10,000 unsigned 64-bit integers, U64, that's what it's called here. On the y-axis, we have the different patterns, and then we have it broken down by individual implementation. One thing we can immediately see, the values vary a lot by pattern, right? We have the fastest one for sorting ascending, fully sorted, versus the slowest one for sorting random, that's 100x difference, right? We have a gigantic spread depending on the pattern, but we also have a big spread depending on the pattern inside the pattern. So for example, if you look at random, the fastest one is this IPN sort in Rust, and the slowest one are the two standard libraries in C++. And there we see a big jump for those that are, let's say, less branch misprediction affected. And otherwise, we also see big differences in the way the underlying algorithmic ideas power different optimizations and abilities to exploit patterns. For example, PDQ sort, from which there is a number of derived designs here, it manages to do n log k for complexity, where k is the number of distinct values. So that's a lot more efficient than n log n. For example, for if you have 21 distinct values, like random d20, you see that in the runtime, it shows up. It's a lot slower. And also random z1, so something like the more real-world random distribution also has duplicate elements, and filtering them out efficiently also is a lot faster than just having to have no information about the data and having to sort it by that, like that. Another thing we see is it's really mixed. It's not like all the C++-based ones are the fastest or the slowest. It's a mix. Really, there's no clear pattern which language is the fastest. It usually plays 1 and 2 are between the IPN sort in Rust and crumb sort in C. And then the C++-based implementations come and go. Generally, in this graph, the C++ standard library ones, I tested, this is Linux, so I just tested libc++ and libstandard C++, but I've also tested the Microsoft one in the past. It's a similar story. Are generally the slowest that I've tested. Let's look at this graph. That's an interesting graph, because earlier I told you that the Rust standard library, as tested here, is a port of PDQ sort. So it's interesting to compare something that was ported from C++ to Rust, and we added safety properties. We saw it was safer to use than PDQ sort. There are some algorithmic differences. So for example, the way it handles already sorted inputs, they are different. And what this graph does is on the y-axis, we have the input length. So each point is a comparison where we ran the benchmark for both implementations, and then we look which one's faster. And then it's a symmetric difference. So if one is, for example, takes 50 milliseconds, the other takes 100 milliseconds, then it's 2 times faster. And if it's switched, it's -2. The one that comes first, the name that comes first, is the one at the top. So in this case, if there's a line is above 0, it means the Rust-based one, the Rust port is faster than the original. And below it is the same thing. And that's symmetric. I want to emphasize that. If we filter out all the patterns that are affected by algorithmic differences, we get this. You see at the y-axis, it went up to 4x. Now it goes up to 1.4x. It's a lot lower. We see some differences for like values below 100. So the y-axis goes from 0 elements all the way up to 10 million elements. And those are also explainable by subtle differences. But essentially, I would say beyond 1,000 elements, that there's no major difference. It comes down to compiler optimizations, subtle things. Let's say also measurement noise. It's not completely noise-free, that measurement method. There are some subtle differences, but we're talking 1%, 2%, 3% in both directions. It's not really a big difference. And the interesting part is, you're right, one is a port of the other. So they really represent very similar code, but one is safer to use than the other. The other port we have is crumb.rs that uses only safe code, interestingly, here, and it's a lot slower. It's way slower. There we see -72% times slower, actually. But this is, again, driven by algorithmic differences. Crumb-sort is a hybrid merge and quicksort. It does a scan at the beginning, and then if it's already sorted, it's done, or it reverses it if it's reversed, and then it uses a heuristic to pick either merge sort or quicksort, and this allows it to be a lot faster in a lot of these patterns. But if you reduce it down to the one pattern where you have no chance of exploiting it, pure, unpredictable randomness, then we still see a big difference, actually, at least for some input length. That's also why it's interesting to measure across the different input lengths. If I just said, yeah, let's measure 10 million elements or 1 million elements, we wouldn't have seen any difference, actually. There was quite nearly matched. But if you look at roughly 2,048 elements, we have a gigantic difference, 2x, 2.4x nearly. what causes that? Maybe it's how it's implemented, maybe it's how it's ported, maybe it's a compiler optimization. But here we see we have one implementation that is a port of the other that is significantly slower, also in those cases where it's not affected by the algorithmic differences, because the Rust port doesn't do that scanning and everything, and this adaptiveness, it just does the quicksort. So that's why this is a more fair comparison. In this other case, we have something where it's very similar performance. So what could that mean? Another thing that happened, because I did these measurements a year ago, the Google people, they looked at their implementation in libc++, or not there, but like the implementation in libc++ of standard sort. And they also noticed that, wait, okay, ordering safety matters. We saw some nasty bugs because of it. And they implemented this something called a comparator sanitizer. So it's not as good as just you won't get ordering safety for your production builds, but you can do what you can do, and what I would recommend you do is you turn on this compiler option, the compiler define. You set a specific compiler define for libc++. I think you might also have to build the standard library yourself, the libc++ standard library, but then you get a lot of sanity checks. It's a lot slower, but for something like a sanitizer built in your CI, that's a good idea to do. And it also does a comparator sanitizer. So where you get, it uses, at the beginning, it builds up a graph of the different comparisons done for the first 100 comparisons and tries to figure out if that's a total order or not, or strict weak ordering to be precise. And that can help you catch these kinds of bugs we talked about. Only one kind, exception safety, mutation safety, they're not looked at here. They also try to optimize it a bit, make it a bit less branch misprediction affected in the partition. But on the Rust side, we also saw some change. They also got, since we've measured the properties and the performance, they got a completely new safe and unsafe stable and unstable implementation. So let's measure it again. This is the same system, same benchmark system, but just newer software. We have Clang 18 now, GCC 14, Linux 6.10. Although Linux doesn't really make a difference here, which operating system. It's just, there's no operating system specific code essentially here. Or there shouldn't be. Here we're comparing the Rust standard library as of today, or as a couple of weeks ago, unstable, sort unstable versus standard sort, which is also unstable. And we see that the Rust-based implementation is significantly faster. So for random patterns, we see something like more than 3x, nearly 4x faster. But essentially across all these 200 tested benchmarks, there's practically nothing where the C++ implementation, standard library implementation, beats out the Rust one for the same kind of task. Unstable sorting, standard library, generic, comparison-based. So we're not looking at SIMD optimized ones or something like this. There's a generic one. So let's talk about some correlations. But because we did a case study, we want to figure out maybe what could we have learned from this talk. And I think one thing we saw quite clearly, the performance you get does not correlate directly to the usage safety. So if it's safe to use, it doesn't mean it's slow or it's fast. There's just no correlation. If it's unsafe to use, doesn't mean it's fast or it's slow. There's simply no correlation in the thing we looked at today. I think this is an interesting question. Whether or not implementing it in a safe subset of the language leads to faster or slower performance. I can't say, because we just have one implementation and it's not really that good of a port, I would say, or implementation. So it's just simply too little data to say anything. Then we also saw no real effect on the implementation safety versus the usage safety. So, for example, is it implemented in some kind of safe subset of the language? Does that imply it's safe to use or unsafe to use? Actually, the safe to use, the implemented one crumbs.rs that's implemented in a safe subset of the language was actually comparatively unsafe to use compared to the ones in Rust, the other Rust implementations that were implemented in unsafe parts of the language. So I think we didn't see a correlation there. But we did see one pretty strong correlation, and that's who's your target audience. If it was written for C++ developers, you didn't really get a lot of safety to your usage safety. So like if you made mistakes, you were on your own, you usually get undefined behavior or other kind of problems. In Rust though, the Rust implementation we looked at, they generally gave better usage safety. For example, ordering unsafety just means you get something that's in some unspecified order because you can't get reasonable results if the comparison function doesn't implement this total order. but you don't just get out-of-bounds reads and writes, which is a lot less bad. Maybe with the new implementation, you actually get an exception. In a production build, you get an exception that tells you, or like a debug build, depending on how you want to do it, you get an exception that tells you, hey, careful, the thing you don't get it guaranteed, but you might get it, or it tells you, it looks like your comparison is in the throttle order. So there's different kinds of safety properties you get in actual real-world usage and how it affects the different target audience here we looked at. So let's come to my conclusion. I would say safety and performance is not a zero-sum trade-off. You get what we looked at today, we saw maybe you don't have to choose as an either-or. Maybe there are some cases where you have to choose. But if you zoom out, if you look at the bigger picture, and you don't think of one specific line of code or one specific optimization, but you look at the problem in a bigger scope, usually there are holistic solutions that are a better solution, which is better in safety, better and in performance. Here we see that Rust users today, and for the last 7 years actually, they get better safety and better performance. It's not an either or, they get both. And you as C++ users, you can have that too. You just need to do it, right? It's not that these implementations, these optimizations are just completely impossible in C++. Most of the implementations that we looked at and that I looked at in these inside these implementations are possible to do in C++. So it's not both the safety aspects and the performance aspects, they're both possible in C++. I would say safety is a question of culture. If you don't care about safety, you're not going to get it. If you want to have something that's safe to use, then you have to care about it. And maybe you think about it in ways of abstractions. For example, in C++, you can write library abstraction. For example, unique pointer, that's a language, that's not a language construct, that's a library construct. And it allows a lot safer usage. And the unsafe parts, they're hidden inside a class or standard vector. For example, most of the ways standard vector is used are quite safe. But if you'd have to do manual memory allocation and reallocation all over the code, that would be quite unsafe to do. And that would lead to a lot more buggy code and security problems, if that's something that's relevant to the code you write. And so what we can think about is you need to care. If you want to have safety, you have to care about it. And you can abstract it inside let's say, library constructs. Not all of the time. It's not something where you can do it all. You will not get something that's equally safe as Rust in C++ just by doing this one coding guideline, usually. You have to have something that's way more full-blown, something like Circle or the things that are proposed currently. But you can get more than zero safety by caring about the way you implement your library constructs. And if there's one thing you can take away from this talk today, I would say that's this. Don't gain 2% by removing a bounce check. Gain 200% of a speed up by changing and thinking about the algorithms and data structures at play. Don't just remove the seat belt in your car to make it fast. Think about the engine. So, yeah, that's the links. You can find the presentation there. You can find the tests and benchmarks in this repository. And with that, I want to say thank you. Are there any questions?
I have a question. I'm actually not unfortunately very knowledgeable in Rust and especially in the implementation of this. So we discussed some specific features like safety, like order safety, exception safety, and there are Rust specific features like, for example, bounce check safety, memory safety, those things that are implemented. When we are talking about the safety and that this safety lives together with the performance, are we also talking about the bounce check safety, for example, for this specific implementation, or it's only those that were listed in the table, where we were like looking more like in the algorithmic and implementation properties, where there were, like for example, mutation safety. What safety we are talking about here? So, I mean, do you also mean a memory safety here as well in the Rust implementations? That's my question.
I'm afraid I'm not sure I fully understand the question. So are you asking whether or not...
How the bounce check enables in those implementation of the library when we are doing the source, for example? How does it look like? So
Okay, so yeah, I think I now get the question. So are bounce checks, for example, enabled? You can't generally disable bounce checks in Rust, so you have to build your own custom fork of the compiler if you want to do that. People have done that, but actually didn't find that big of a difference in real-world code like databases and whatnot in terms of performance. Because bounce checks, actually, they can prove things to the compiler, where if you do a bounce checks, the compiler can generate more efficient code. Not all of the time, but so there's a correlation there. But essentially what we have here, it's Rust code, that's vanilla Rust code. There's nothing turned off, you can't. But what it does, the implementations that were the fastest actually, that we looked at, they do unsafe operations. So they are allowed to work with pointers where they don't have to do a bounce check, but they have to do it in a way where if you as a user of sort, if you can somehow use it in some kind of program, for example, you mutate it, you throw an exception, everything like this, you have a broken comparison function. All of these things are considered safe usage, and they are not allowed to lead to unsafe behavior. But you can, for example, if you do the partitioning, you do Lumutu partitioning, where you just scan through the thing once, you don't have to do any bounce checks, because you know you're going to go from the first element to the last element, and you can access each element without a bounce check, because you know you're not going to compute user-defined offsets. You just know which offsets is going to be. In your head, you can validate, and even the compiler sometimes can validate that, yeah, okay, I don't need to do bounce checks here, and we have walking through the array once. So I hope that answers your question.
Yeah, thank you. That's what I meant. But yeah, thank you.
One question I have. What is your view on this safecpp.org? Where this project is some kind of library working along with the CPP organization to bring the REST features inside C++, like all the borrow checker and all this stuff.
Are you talking about what Sean Baxter is doing with Circle?
Is safecpp.org.
Yeah, okay, because there's other efforts like Hilo and whatnot. I just want to make sure. What are my thoughts about it?
Yeah. So what do you think, like, when someone is using it, like, so because someone can get a conclusion, okay, I think REST is better, let's move to it, but someone say, okay, for me it's not feasible to move to REST, and should I look into something like safecpp.org and something like that? So what do you think about that?
It's a valid question. I think a lot of projects face that question where they are, okay, we might be under some kind of pressure externally, internally, or like we just want to make sure we have less bugs because bugs are also expensive. You're right. If you have something you're debugging in production or you have a security critical issue, that's usually quite expensive. So management also cares. And how do you modernize certain parts? For example, modern C++ tried to sell us on this promise of like use these new library constructs, unique pointer, not a raw pointer, and yeah, that's an improvement. It doesn't get you all the way. You will have some areas that are where it doesn't help you with, but it's a big improvement. So I believe personally in incremental improvements. I don't say everything has to be changed overnight. And I think a lot of people in this room also have legacy code bases in C++. You're not going to just say, yeah, let's just rewrite it all in Rust. I think that's stupid. So that's why also in this talk I don't want to give you the impression that just use Rust, it's better. I'm just telling you, you can have more, right? These guys, they get better safety and better security, and you can have that too. Not to the same degree, but you can have it in meaningful parts. You don't need to be 3 times slower and less safe to use, right? That's a bad trade-off to have. So coming back to this question of like, what about efforts to bring Rust features like borrow checking that make it safer to use into C++? I think if you are today have some piece of code that's like a file decoder and you get user-generated content and you want to make sure it's safe and doesn't get out of bounds and whatever, my recommendation would be don't wait for safe C++. It's not in a good state today. Write that module in Rust and interoperate with it with your C++ code. Don't rewrite all of your Rust C++ code, but if you have to have some security critical thing and you want to make sure it's really robust, you're better off writing it Rust. And when you are starting new, if you have something existing and porting it over, that's kind of a hard sell, because with this safety thing, the safe C++, what it asks you to do is rewrite all of your C++ code. There's no gradual process where you can just say, maybe you can do one module at a time, but you can't do just one function at a time usually, because you get a different standard library that doesn't exist. So someone has to write that new standard library. And that standard library has incompatible types. As far as suddenly your standard vector is not compatible with your standard vector in another module, and now you're essentially linking 2 separate languages. And that kind of sucks. And so I would say the goals it has are admirable. I think where it is today is 10 years behind where Rust is today in terms of ergonomics. A lot of work has gone into making Rust more usable because these lifetime annotations are actually really complicated and to reason about if they don't get elided. So, but right now in this safe C++, you have to mention them all over the place. It doesn't give you a elision. Yeah, and maybe you will get there in 2 or 3 years. But as of today, I personally wouldn't use it. I think it's an interesting goal, and it asks a bigger question of, okay, we are stuck with C++, but it has issues. How do we move forward? I think one issue is care about safety. We saw that these sort implementations, they don't have to have ordering safety result in out-of-bounds reads and writes. It's just based on the attitude that no, these 2% are worth too much to give up. We're not going to change, which is ironic because they could gain 200% somewhere else. They just rethought their algorithms. But this is where we are today, right? So I would say it's a noble goal. There are other efforts that I think are a little more promising, but overall, it's a hard sell. If you need safety, rewrite a module in Rust. If you don't care about it and it's not important for you, keep on going with your regular C++. I wouldn't recommend just wholesale switching over to this new safety thing, which is just too young. It's just not mature. It's not usable. It's more of an experiment. The standard library that it needs, the second fork of the standard library, which is incompatible, it doesn't exist. So how are you going to write software without a standard library? So it's more of a thought experiment than a actual, concrete, usable thing. But it's an interesting direction. I hope I didn't murder your question.
I really liked your message in the end, that you can get the safety without having to pay for it if you're clever about the algorithm. And I found the example for the sort really convincing. But the skeptic in me is thinking that maybe you just got lucky with the sort there. Maybe like this is not true in the general case. And in particular, if I were to put one of the examples that you showed is like the strong exception safety, right? Where you sometimes just have to make the copy to get the safer behavior. So what would you say to that skeptic side of me to like, to take away those worries?
I think they're founded, actually. I don't think they're completely unfounded, your worries. So I don't think you will always have a lucky situation where just think a bit bigger and you will find a nice solution which gives you all the things you want. That's not always going to be possible. Sometimes you will have to make hard trade-offs. But my idea and something that changed as I was doing this research is actually there are way more places where this trade-off doesn't have to happen. Where if you zoom out a bit, you can have more than where you are stuck in a local minimum right now. So I'd say there are a surprising number of places where all it takes is to actually try. And I think other people have tried and they might not have gotten as far in some things. Sometimes it's luck, sometimes it's building on top of the work of others, but I think we shouldn't give up trying. And I think we as C++ people as a community are not trying hard enough.
I can get behind that, yeah, thanks.
Okay, well done. Thank you.